Hello, ladies and gentlemen. Mr. Dorfler here with your daily dose of Dorfler. And hello to my fellow teachers who have stopped me in the hallways and said how much you enjoy watching my videos on an almost daily basis. Salute to you. I'm here for more, and I've got plenty more in store for you as the year progresses. Anyway, we are here to start off the second half of the chapter. And this time we're going to be looking at light again. However, we're going to be looking more at a kind of physics side of light. Now, I'm not going to do any calculations, but there is going to be some terminology that will most likely be new to you. And don't fret it. Just be, staying on top of the terminology. Make flashcards if you have to. Stay on top of your notes, and you'll be A-okay. All right? Now, let's talk about reflection of light. Now, that is a seemingly basic concept. We see reflection of light all over the place, all the time, but there is a lot that happens with the reflection of light and what is actually going on and what we are actually perceiving and the angles and geometry, which I know you are all excited to introduce another math course, but hey, they're all kind of tied pretty tightly together. So let's get into the notes. Stay with me. If you get behind, hit the pause button. Make sure you get everything written down, and then we'll keep on going. Anyway, all objects reflect and absorb some light. Right now, I'm wearing a purple jacket. I'm also wearing blue jeans. I have various components on my desk and in my desk. Okay, all of these objects are going to reflect or absorb some amount of lights and some frequencies and wavelengths. Okay, the surface of the object is what is going to determine the way light is reflected. If you think about mirrors, okay, mirrors reflect light in a way that allows you to see an image of yourself or other objects that are in front of the mirror. So, what's happening is we have light rays that are bouncing off of these surfaces. Light rays are lines in space that matches the direction of the flow of radiant energy. Okay, so whatever direction the flow of radiant energy is going, that's the direction of the light rays. Okay, this is another model to help describe light. Especially when we start talking about reflective surfaces, we need to have the ability to put something tangible, like a line, to help describe where light is going. Light rays move in the same direction as the wave model of light or as the path of photons in the particle model. So we're bringing stuff from earlier on in this chapter back into the forefront. This light ray model helps describe reflection, also refraction, and also the behavior of light. Here's where we start getting into the geometrical optics part of it. It's a study of light using the light ray model of, light. So we have to use geometric optics. We are able to look at the path of light rays and show that they are displayed on geometric drawings called ray diagrams. This is a study of light, but it does not give the full picture of the complex nature of light. Now, in the last section, we've already discovered just how complex light is. It does not like to follow, what we consider real world stuff, but it is real world stuff. So we need to understand it better. So let's talk about how light reflects on various surface types. On smooth surfaces, okay, light is reflected into a single new direction, as we see on here, if you see where my mouse is over on the right-hand side. When we have a situation like this, we have what's called an angle of reflection, which is defined as the angle that light rays reflecting off a smooth surface. Okay, so we have to look at these angles that is created by these light rays. We also have what's called the angle of incidence. It's defined as the angle of the light rays striking a smooth surface. So angle of incidence is striking a smooth surface. Angles of reflection are reflecting off of. So this would be the angle of incidence. This right here would be the angle of reflection. The angle of reflection is equal to the angle of incidence. This is the law of reflection. Then we have what's called the normal, okay? The normal is defined as the line in which the angle of incidence and reflection are measured. So typically it's going to be right here right here in the middle that's going to essentially divide the angle of incidence and angle of reflection equally. So again, looking at this image right next to my image here, this incoming light, this is the angle of incidence, incoming incidence, okay? And this is the angle of reflecting light. As you see here, noted here, these angles are equivalent, okay? Rough surfaces, however, we get something a little different that's occurring here. Light is reflected in completely random directions, as we see here in this top image up here. This is called diffuse reflection. Some examples that we have diffuse reflection are when light is reflected off wood, reflected off certain cloth, as well as skin. Okay, even though it feels smooth, there's some very small imperfections in all of those items, and all of those imperfections are going to cause these light rays to bounce off at various directions. Now, we've mentioned mirrors very briefly in today's discussion, so now we have to dive deeper into mirrors, okay? You might think that, oh, they are so basic, they're so simple. Do my hair in front of them, I put my clothes on in front of them, whatever. There's a lot going on with mirrors that you may not know, a lot of science that is happening in a mirror. So let's look at the principles of mirrors. They reflect light as described by the law of reflection that we just talked about. Light reflected reaches your eyes as an image of what is being reflected. There are two types of images that are being reflected towards you when you're looking at a mirror. We have a virtual or real image may appear in light reflected in a mirror, and a type of image depends on the type of mirror that is used. Let's look at an example. Okay, a copy, when you see yourself in a flat mirror, a copy or twin image of yourself is seen on the other side of the glass in the mirror. So as you see this individual here, this is the actual person, and he's seeing himself on the other side of the mirror. In addition to yourself, you're also being shown or reflected the space behind you. And remember that the angle of incidence is equal to the angle of reflection whenever you're looking at a mirror. The image on a flat mirror is going to be flipped from left to right. That's why it's called a mirror image. When you raise your right hand in front of a mirror, it's going to look like your left hand is being raised, okay? It is just a flip-flop version of yourself and your surroundings, okay? Then, sticking with mirrors, we have convex and concave mirrors. And these are fitting in the category of curved mirrors. Curved mirrors cause light to be reflected in different directions because the line perpendicular to the mirror, which is, remember, the normal, points in different directions. It distorts images so that they are smaller or larger than the real object. Convex, concave. Now, convex, if you look up here, are the ones that bow out, okay? Concave has the word cave in there, so it caves away from the direction of the lights are coming in. Okay, so let's look at convex first. These are curved mirrors that bulge out and makes objects appear smaller than they actually are. If you look at a car's side mirrors, it always says objects in mirror are closer than they appear. Well, that's because they have a slight bend or bulge that is bulging out, and it appears as though an object or a vehicle coming up put aside is a little farther away when in fact it's right there. That's why you can't rely on your side view mirrors 100% because they distort the reality slightly. So you always need to be turning your head when you are driving. Good point for you new drivers. Those drivers ed teachers would be very happy with me, I can imagine. Then we have concave mirrors, okay? These are curved mirrors that are indented or pushed or, you could say caved in. What these do is these magnify objects to make images that are larger than the objects themselves. When we have reflecting telescopes, if you ever imagine why we have, these tools and devices that allow us to see images that are so far away, but when we look through them, they appear much larger than what our normal eyes are seeing. That's because they use a series of mirrors, mostly concave mirrors, to help enlarge objects for us. Same concepts go with glasses. Okay, we use convex and concave angles, essentially lenses that allow for different images to appear smaller or larger. And here's just looking at here where my picture is. That'd be a convex mirror. See how it's bulged out and everything looks a lot smaller. Here we have a concave, which is pushed in almost similar to a bowl. What just happened? Okay, wasn't sure what happened there. And it makes everything a lot larger. It's actually really cool about concave mirrors is we have a device here at school. Fortunately, you can't really see it, and the camera wouldn't do it justice, where we have a concave mirror bowl with a top, and when you put an object right in the center of that bowl, put the lid on it, the light reflects in such a way that it appears as though that object is floating in midair above the bowl. It's kind of how like holograms are made. Okay, various light angles, but it's actually really a really neat thing to see because your mind just can't perceive that. It looks real, but it's not. You try to grab it and it just vanishes. Really nifty. Okay, we talked about virtual and real images very briefly. Let's talk about them now. So a virtual image is defined as an image from which light rays appear to diverge, even though they are not actually focused there. Okay? A virtual image cannot be projected onto a screen. For example, seeing your reflection in a flat mirror. Okay? Light from the mirror is reflecting and reaching your eyes in all directions. The brain interprets the light as if it traveled in straight lines from an object to your eye. You perceive an image of yourself behind the mirror. A virtual image of your reflection in the flat mirror appears to be as far behind the mirror as you are in front of it. So, when you're looking at a mirror, you perceive yourself as being actually double your distance away than you are actually from the mirror. So, for instance, if you find yourself, standing 2 feet in front of a mirror, your mirror image is going to appear as though it is 2 mirrors on the other, or 2 feet on the other side of the mirror. So therefore, it'll appear as though you and your virtual image are approximately 4 feet apart. All right. So that's what a virtual image is. Okay. These light rays appear to diverge, even though they are not actually focused there. Real images are defined as an image that is formed by the intersection of light rays. A real image can be projected onto a screen. Light waves and real images. A real image appears when light rays come together. It can also be said that light rays exist at the point where the real image appears. Virtual image appears to exist in a certain place, but no light rays exist there. When you look at an image seen from a movie projector, so if and when you are in class and you're having your discussion projected onto the board or a screen, that is a real image. Okay, so these are light waves essentially. All right. One of the last things we're going to talk about is color. Okay, when we see colors, what we are seeing is a perceived wavelength of visible light that reaches our eyes. Okay, the color of a rose flower. Okay, the light that is ambient or around us is going to strike the leaves of the flower and reflects light with a wavelength of about 550 nanometers. Okay, if we were to look on an electromagnetic spectrum and have a really broken down version of that, we would see that the wavelength that is 550 nanometers is about where the color green lies on our color scale in the electromagnetic spectrum. So the leaf is actually absorbing all of the other wavelengths, and it does not reflect those other colors that are in the visible light spectrum. The reflection of the wavelength at 550 nanometers is the light wave that enters your eyes and what your brain interprets as the color green. So really what we're seeing in terms of color are reflections, okay? We are seeing reflections of various wavelengths of light on various objects in which they also absorb other wavelengths. So that's what's fascinating about light, is what we see is really just reflections of various wavelengths. Okay. Now, light strikes the rose petal of the flower is going to reflect the wavelength of about 700 nanometers. Okay. So, again, looking at the electromagnetic spectrum scale, we find that the 700 nanometer falls right about where the color red appears to be. So the rose petal absorbs, just like we saw with the leaf, all of the other colors in the visible light spectrum, but it tends to reflect the wavelength at 700 nanometers, which our brains perceive to be red. So oftentimes we can use filters when we are trying to obtain various color combinations. So colors through filters, what these do is they transmit the light of a particular color transparent filter, and it's going to absorb all other colors of light. For example, the rose flower viewed through a green colored transparent filter. The green light is transmitted through the green filter, and all the other light is absorbed. Leaves on the rose flower will appear to be green. All other parts of the flower appear to be black. So putting a green filter on a white light source and focusing that on a rose, the green leaves will be still green, but everything else is going to be looking like it's a dull black color. Now, if you were to take the rose flower again and view and shine the natural light through the red filter, the red light is going to be transmitted through the red filter, and all the other colors will then be filtered out or absorbed. The rose petals will be red like they are before, but we will then see everything else appear to be black on the other parts. And we see that example here, okay, where here we're shining light through a red light filter. That red light filter is going to absorb pretty much all of the other wavelengths except the red light. The red light is going to strike the flower and the rose petal. It's still going to reflect that red light, but everything else on the plant is going to appear to be black. Another example is we probably see all the time. We see it on a daily basis for some of us. We see a lot of times when there is rain occurring and sunlight is out. We see sunlight through a prism, okay? This is going to separate sunlight into a rainbow. And the sunlight actually contains all of the wavelengths of visible light in the electromagnetic spectrum. And this prism causes the light to essentially split apart from its normal white light into the various visible colors that we see in a rainbow. Lastly, we're going to talk about mixing colors. Most color that we see are not pure colors, but rather mixtures of colors. A lot of times if you have a printer at home, okay, that is a color printer. Oftentimes you may only have 3 different colors that you have to put into your color printer. Those 3 different colors are going to essentially mix together in various proportions to basically come up with this multitude of colors that you can print out. So we have additive primary colors, which are red, green, and blue. And mixing 2 additive primary colors can produce 3 types of secondary colors: yellow, cyan, and magenta. Mixing all 3 of the additive primary colors produces white light. Now, when we mix the subtractive primary colors, so subtractive primary colors will be yellow, cyan, magenta, so the secondary colors. Mixing 2 subtractive primary colors to produce 3 types of colors: red, green, or blue. Okay, so primary colors. However, when we combine all 3 of the subtractive primary colors together in equal proportions, causes all the light to be absorbed, and what we see is black. Black is not a color, but the absence of color. So here what we have is we have red, green, and blue coming together right here, here, and here, okay, to form our secondary colors. And when all 3 of those colors come together, we get white light. However, if we take all 3 secondary colors and start mixing them together in certain ratios, we get red, green, and blue. But we try to mix all 3 of those subtractive colors together, we get color black, which is the absence of color. All right, so that is going to wrap us up for 16.3. Make sure that you do your 16.3 review and get it turned in tomorrow. And then we will do our last bit of note taking in the next time you see me. So have a good day, everybody. I will talk to you all later. Bye-bye.